Have you ever just stopped and thought about what's happening inside your computer? I mean, it's kind of wild. You click a mouse, you type on a keyboard, you watch a video, and somehow this box of circuits and wires just gets it. But how? Really, how? All right, let's actually dig in and figure this out. We're going to peel back all the layers today and get to the bottom of that one big question. How can this thing, this inanimate machine, understand something as beautiful and complex as, well, this? I mean, how does it see the different shades of pink, the light hitting the petals, the whole feeling of the scene? It seems like it should be impossibly complicated, right? But the answer, well, it's actually shockingly simple. Yep, you heard that right. Everything your computer does, displaying that photo, playing your music, even just letting you move your mouse around, it's all built on the idea of a plain old switch. Think about it. A switch can only be in one of two states. It's either on or it's off. That's it. And that simple choice, on or off, is the only thing a computer really understands. You've seen these symbols your whole life, probably without even thinking about it. The little line means on and the little circle means off. This incredibly simple two-state system, that's the key to everything. So how do we get from a simple on or off to something that actually means something? Well, we start by giving those two states a name, and that brings us to the computer's one and only native language. And that language is called binary. It's super simple. We just assign a number to each state. We say off is 0 and on is 1. That's it. Each one of those zeros or ones is called a bit, which is just short for binary digit. So every single piece of information on your computer, no matter how complex it seems, is really just a super long sequence of these bits. So how on earth do we make sense of these long strings of zeros and ones? Well, since there are only two symbols, we use what's called a base 2 system. And all that means is that each position in a binary number represents a power of 2. You always start from the right and work your way left. Okay, let's actually try one. Take the binary number 10111. What does that even mean? So remember, we read it from right to left. The first spot on the far right is the ones place, 2 to the power of 0. The next one is the twos place, then 4s, then 8s, then 16s. Now here's the trick. You only add up the values where you see a 1, where the switch is on. So we have a 16, we skip the 8, then we have a 4, a 2, and a 1. So you just add them up. 16 plus 4 plus 2 plus 1, which gives you 23. See? That string of ones and zeros that looked totally random a second ago, it's not random at all. It's just a different way of writing down a number we already know. It's basically a code, and now you know how to crack it. Pretty cool, right? Okay, so computers can count using ones and zeros. That's neat. But how does that simple counting let them represent our messy, complicated world? Let's see how this thing builds on itself. So when you press this key on your keyboard, you see the letter A. For us, that's just instant. We don't even think about it. But to the computer, it's nothing more than a number. To be specific, it's the binary number 10000001. There's actually a standard code, called ASCII, that assigns a unique number to every letter, number, and symbol. So the letter A is just a very specific pattern of on and off switches. Same exact thing here. You see the number 9. Easy. You've known it your whole life. But what does your computer see? Just another binary pattern, 0001001. See, it's all about these agreed-upon codes that translate our world into the only language the machine can possibly understand. And this doesn't just work for text. I mean, take sound. To us, sound is a wave, right? It has peaks, it has valleys. And your computer captures that sound by taking thousands of little measurements every single second. It records each one of those measurements as, yep, you guessed it, a binary number. And that beautiful picture of the cherry blossoms, same deal. It's just millions of tiny dots or pixels, and the color of every single dot is represented by a binary number. When you get right down to it, everything is just ones and zeros. So now we know what the data is. It's all just ones and zeros. But how does it actually get from point A to point B? How does pressing that A key on your keyboard make an A magically appear on your screen? Well, this diagram lays out the whole journey, and it really happens in 3 main stages. First up is input. You press the A key, and that sends a specific binary signal into the computer. Next is processing. The computer's brain, the CPU, gets that signal and figures out, okay, what do I do with this? And finally, there's output. The CPU sends a new set of binary instructions to your screen, telling it exactly which little pixels to light up to draw the shape of the letter A. The whole path, from your finger to the screen, is just a constant flow of ones and zeros. All right, so we've got this beautiful, elegant system that's built on a constant flow of on-off signals. But what happens when that flow gets interrupted? Understanding this really basic idea can actually help you fix some real-world problems. Oh man, we've all been there. You power up your computer, you can hear it running, but the screen is just blank. Nothing. It's so frustrating. But if you just think in binary for a second, it can actually help. The problem is simple. There's no signal. No ones and zeros are making it to the screen. So what's the first thing you do? A simple restart. Sometimes that's all it takes to get the flow going again. If that doesn't work, check the most basic switch of all. Is the monitor's power button actually on? Still nothing? Okay, now it's time to check the physical path the signal takes. That's the cable running from your computer to your monitor. And this right here connects everything back to our main idea. A loose cable is really just a giant broken switch. It's stuck in the off position, period. If that stream of ones and zeros can't make the journey from the processor all the way to the screen, you get nothing. No signal, no picture. It's really that simple. So, when you really boil it all down, this is the big takeaway. The absolutely incredible, complex, vibrant, digital world we all live in, it's not magic. It's just the result of billions and billions of tiny little switches, all flipping on and off, 1 and 0, at speeds we can barely imagine. It's a system of unbelievable complexity, built on the simplest idea you could possibly think of. And that kind of leaves us with a final thought to chew on. From the way traffic flows in a city to the way a colony of ants organizes itself, where else in your life do you see something incredibly complex that's actually built on just a handful of really simple, basic rules?